Hey there, my name is Alejandro, and welcome back for day 161 of me doing a daily LeetCode challenge until we reach 1 year's worth of green contributions here on GitHub. So today's problem is for December 24th, 2024, and let's get straight into it. Okay, today we get LeetCode hard from 3203, find minimum diameter after merging two trees. Okay, there exists two undirected trees with n and m nodes. Okay, numbered from 0 to n-1 and 0 to n-1 respectively. You're given two 2D integer arrays, edges 1 and edges 2 of lengths n-1 and n-1 respectively, where edges 1 of I equals a bi indicates that there is an edge between nodes ai and bi, so I'm guessing these are, okay. In the first tree, and edges 2 of I equals ui to vi indicates that there is an edge between nodes ui and vi in the second tree. You must connect one node from the first tree with another node from the second tree with an edge. Return the minimum possible diameter of the resulting tree. Okay, the diameter of the tree is the length of the longest path between any two nodes in the tree. Okay, so I must pick one from here and one from here, right? So n times n possibilities, is it too slow? Okay, yeah, they're both 10 to the 5. So if I try every single possible pair, that doesn't work. Okay. Well, it's a LeetCode hard after all. Of course, it's not going to be brute forceable. Okay. So there's going to be some. So yeah, DP would be literally just like, try them all and return the best one, right? There's got to be some way where it's like, you're able to knock down levels or so on to make it like, linear or whatever. Probably some greedy idea, right? Tree hard problems are often greedy by nature. Okay, so let's look at example 1. Tree 1, 0, 3, 2, 1, and 0, 1. Output is 3. Oh yeah, because if you do this and to here and to there. So what you want to do, connect the shortest path in the first one and the shortest path in the second one? We want the shortest path from the root. Wouldn't you? So do you want like the shortest path from the root to a leaf? Yeah, it's undirected, right? So you don't want to just go to this guy's leaf because this guy goes all the way up to the root, right? And you should you always connect to the root of tree 2? Because if you don't connect to the root, you can always go to the root and then go to the other path, right? So you should always do the root of one tree with okay, let's see. We can obtain a diameter of 3 by connecting node 0 from the first tree with any node from the second tree. Yeah, so what I'm seeing here is you're either going to do the root of the first tree or the root of the second tree, right? So you can even do both cases, right? One is like you do the root of the first tree with every other node in the second tree, as well as the root of the first tree with every single other node in the second tree. And it'll be linear time complexity. Okay, so there's already that idea, right? Because if you connect something like here with something that's not the root, it's able to always go up to the root, right? But I guess if it's midway between a path before, right? If you have A to B to C, then maybe it makes sense to point to B here, right? Because from B you're only able to expand one way. Okay. So maybe it's not quite so simple. Okay, let's look at example 2. Okay, yeah. We can obtain a tree of diameter 5 by connecting node 0 from the first tree with node 0 of the second tree. Okay, let's pay attention to their end degrees and stuff like this, right? Things that can give us cues. 0 has an end degree, or we'll say degree, right? Because really it's 0.2 pointed by doesn't matter, right? So if anything, it has an end degree of like 6, right? And there you go. This has an end degree of 2, right? Or like a degree of 2. Like it's basically like, everything's end degree is basically its out degree, right? Because it's undirected. So we can just count the degree, which will be the end degree plus out degree and so on, but it will still keep the same structure. So like this has a degree of, we'll say a degree of 3, but really it'll be 6. Degree 1, 1, 1. Both of these have a degree in 1. So here, it wanted the minimum degree node. Would that essentially be the answer? the minimum in degree node here, plus the minimum in degree node here, and then plus 1 for the edge that connects them. No, in degree can refer to multiple nodes, right? So if I grab this guy's in degree, it's 3 or 6, whatever, and when I connect it, the paths are just 1, yeah. In degree is nonsense information. Yeah, but I do want something like the least reachable node, right? This is an interesting problem. Of course, for Christmas Eve, they gotta hit us with a LeetCode hard, eh? That's just the LeetCode way. No breaks, no breaks. They ain't feeling merry this Christmas. Well, no what? No worries, no worries, no worries, no worries. What are any of y'all celebrating? Merry Christmas. I hope you have a wonderful family dinner. And yeah, and tomorrow will be Christmas Day, and so maybe I'll wear a Christmas hat. We'll see. You know what? For today's, we'll wear this little hat that I do for the Advent of Code challenges. And you know, tomorrow if I have a red Christmas hat, we'll just wear it. And there we go. We'll make it a special occasion. For the 24th, we'll just wear this. For the 25th, we'll put the red Santa hat on. So yeah, there exists 2 undirected trees. Yeah, interesting. So like, there's going to be some greedy idea, right? So let's pay attention. Here we pick the 1, which is a leaf, and has the smallest in degree, right? Here we pick the 0s. Let's analyze this, right? This has an in degree of 3. And this guy of 3. So the length of the longest path from this guy is 1, 2, 1, 1, 2, 1, 2, right? From here it's 1, 2, 3, 4. From here it's 1, 2, 3, 4. From here, yeah. But if I do a DFS, well, maybe I can cache results, right? I can do the longest path from a specific node. And cache the results for that, right? For example, like, you know, the longest path from 0 is the maximum between 1 plus the longest path from 2, 1 plus the maximum path from 3, 1 plus the maximum path of here, right? And then it's like, you know, from here it's like, you know, if you have yeah, but then it's gonna be recursive, right? So should I have like a topological ordering of the elements, if anything, and then start DFSing? Yeah, for example, topological here would be 1, 0, 3, and 6. Well, I guess it's undirected, right? So it doesn't really make sense. Everything is a cycle. But there's going to be some idea like that, right? You're going to try to get the longest path from each node, and they're each going to be like kind of dependent on each other, right? Dun-dun, 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 dun-dun. Adjacency list 1, 2, we'll say default dict of what? We'll do a set for each, default dict of set, and then for it would be in edges 1, adjacency list of a.add b, adjacency list 1 of b dot add a, for u comma v in edges 2, c list 2 dot add v, v dot add u. So yeah, so we want to perform some kind of DFS, right? So we want to do like, depth shortest paths. Because here's like, okay, let's analyze it, right? The length of the longest path from 0 here is 1, 2, 1, 2, 1, 2. It's 2 for them, right? But for this guy it would be 1, 2, 3, 4. For this guy it would be 1, 2, 3, which is more than 2. This guy would be 1, 2, 3, which is more than 2. Yeah, so this guy is the one that has its outwards path is as small as possible. For this one, it's probably the same, right? Is this? Yeah, this is just a clone of the same graph. So this one, it's the longest path from that node is minimal out of the entire graph, right? So that's essentially the queue. The queue, not as in queue. I mean it as in queue, like this. That's our queue. But I realize in computer science that can mean something else, right? So yeah, because we can afford to be linear on these things. So yeah, so we can't just start exploring every path. But if we cache our way through the DFS, we should be able to do it linear for both trees, right? Never do any repeated work. Right, so like from 0, maybe I should topologically sort these elements just for fun. So that way I can explore from the one that has the least amount of dependencies, right? But otherwise, what I can do is like for each node, I can say, okay, here we'll just focus on the very first graph. In range. Wait, why is it of length n minus 1? Oh, because there's n minus 1 edges? Yeah, so that's also interesting, right? Because it kind of implies that there's no really cycles, right? And plus it's a tree, which means it's not like, disjoint. So yeah, they really say tree so that you can know that essentially the graph is like kind of connected and there's n minus 1, so it's like you can be confident that there's no cycles. They're very smart about that. Really, the word tree is really there to just tell you like, hey, there's no cycles in this graph if you're smart. Okay. This problem is very doable. We just gotta do it. Okay, for node in range, so here we'll say n is equal to n comma m is equal to length of edges 1 plus 1, as well as length of edges 2 plus 1. For node in range n, what shall we do here? We'll do, here we'll say visited is equal to a set, right? If node and visited continue. Otherwise, visited.add node. We want to be able to DP our way, right? What we want to be able to do is essentially, we need to have a function here that says def get longest path from node 1, from node. Here what we need is like a self.d1, self.d2. We need to know the graph that it belongs to too, right? Then we could get longest path from node 1. node in self.d1 to self.d1. Otherwise, the only thing is I don't want to be stuck in an infinite loop. I need like a visit. I need to do this properly, right? Maybe the ordering does matter. Maybe I should topologically sort these elements. If I topologically sort them, right? Then I don't have to be worried about the order of visitation. Or creating, or yeah. Like basically, if I sort them topologically, I'm able to just go down the flow, right? Almost treat it like a tree, basically. I think that's kind of the idea here, right? Because here it's like, you know, if I start from 0, it's really annoying, right? I go to 1 and it's like, okay, calculate the shortest path, and then 1 is going to be like, okay, calculate it from 0, right? If I do it topologically, okay, here we'll do def topological sort nodes, adjacency list. Here we'll say in degrees maybe I do edges. Right, it's undirected. Remember that's undirected. Undirected. How does topological sort, right? Essentially, it's like order equals this. Everything has at least one edge. Is the guy with the most edges necessarily the root? No. This isn't a root. Or maybe like this. Actually, no, yeah. That could be all of it. But then any node can be the root, right? Say that's... Maybe topological sorting is kind of useless here, right? You can just do it from anywhere. But no. It would be nice to do it from a guy like this. But then from, like, if you do it from this guy, here you face the same issue, right? Okay. Yeah, I need to be able... Essentially, I need to be able to build my tree, right? So that's like, I need like a root, yeah. Because the idea is simple, right? I want to be able from each node essentially get what is the length of the longest path from that node, right? The only problem is that it's dependent on others. Maybe I can give it a band set. or a visited set. Yeah, the trick is to do a visit set, right? Like from 0, essentially it's like, you know, I want to say the minimum, the maximum between here, here, and here. And these guys need to capiche the fact that, hey, 0 is visited now. Don't look at me anymore. Get longest path from node. What I need is this. I need def get longest path from node helper. Return get longest path from, so this should take a self. This will be self.this with the node. We gotta do a self.memo 1, self.memo 2 if anything. Right, and then I can pass the memo and so on. So yeah, get longest path from node. Node. Okay. So this, there we go. So now we have 2 helpers. For node 2, it'll be self.memo of 2. So yeah, the fact that we have 2 trees, 1 function for each. So now we can build this more generically. If node is a memo, return memo of node. Otherwise, here we'll say, hey, maybe we do a BFS reversal here, right? Let's do that. Elections.deck. We'll just do the node. The length of queue is greater than 0. Node is equal to greet up top left. Maybe this passes in an empty set, and this passes in a visited set. Or no, let me think about this. How do I do this, right? The point is, like, it's undirected. This is annoying as heck. I don't want it to go back. I need to use a visited set of some sorts. Q is equal to collections.deck. length equals this. Res is equal to max of path lengths. Self.memo of original node equals res. We'll do self dot. Okay. Here, yeah. Adjacency. So yeah, this will get passed in the adjacency list. Of node this. Because here I want to do minus visited. Right, the point is like here, if I'm going to look at yes, like how do I stop, right? Like the point is simple. Like I want to say like, hey, this guy's the max of this guy's path length, this guy's path length, this guy's path length, and then all of it plus one, right? But it's like, yeah, I need like a topological ordering. I need to have it. I need to treat this like a tree. So yeah, what I need to do is be like, hey, this is my root node. This is its children. This is its children. This is its children, right? And then it's like, the point is that I need to define something like this is a leaf, 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 right? I need a base case, right? Where it's like, you know, I want to treat certain nodes as leaves. Can I treat nodes that just have one connection as leaves? Right? If their in degree is 1 or their total degree is 2, can I always treat that as a leaf? Like, will there always be a tree for me to construct where those are all the leaves? Right, like here, for example, I could have this as my root. This is a direct leaf child. This is a direct leaf child. This is a direct leaf child. Direct leaf, direct leaf. Right? So the point is I need to build the tree. Once I build the tree, then I can do my DFS idea and it works, right? Because now there's a base case to the recursion and it's not forever. That's what I need. That's really what I need. In degrees 1, in degrees 2. Each node has at least Here we'll do def is leaf. There are n minus 1 slash n minus 1 at n nodes, or n minus 1 edges. Since we know graph forms a tree, we know there are no cycles, and that the graph forms exactly one strongly connected component, not disjoint. So if a node's total degree is exactly 2, then say it is a leaf node. Return degrees 1, self.degrees 2. Self.degrees 2, u plus or equal to 1, the degrees 2 of v plus or equal to 1. Def is leaf 1, comma node, return self.is leaf with node and self.degrees 1. Def is leaf 2, self comma node, return self.is leaf node comma self.degrees 2. Well, here we'll do self.degrees 1, degrees 2, degrees. Here we can bring this down over. To here. No, but then the only problem is that, oh my gosh, it's the reverse problem, right? Because then what if we want the longest path from a leaf? Basically, I need to do a DFS at some point, right? Everything forms one strongly connected component. Let's think about it that way. Everything forms one strongly connected component. So if I do a DFS or a BFS, right? We can do BFS, whatever. I'm bound to hit every single node. Right, like I can't do a DFS from every single node. That's just not possible. I cannot do that, right? Because if worst case I call DFS from every single node, get the longest path from that node. Like it would be nice as I do the BFS to be able to update other nodes longest paths, right? But it's just, it works in two ways. Again, it's just annoying that the graph is cyclic. Yeah, sorry. I need to drink more water. The graph is naturally cyclic. Are there hints for this problem? Yeah, there are 4 hints for this problem in case we need them. Yeah, but I get what we need to do. We need to get the longest path from every single node and grab the shortest one. Yeah, because I'm going to infinitely call, right? Oh my gosh. It's annoying. Right, because to get the longest path from 0, I need 3s, and for 3s, I need 0s. Right, and I can do it for a single node, but then it's just like, okay, I've only done it for a single node. Unless I topologically order, and then it's like, yeah, topological sort doesn't work here. No node has an in degree of 0. But I guess we can do a degree of 1, yeah. It doesn't matter which node you pick, right? You do actually no. It matters that you pick this one. Yeah, but again, this one has the shortest distance out of anyone, right? Maybe you define the edges to go this way. The point is that you mark this visited. I can't just do it for every single node. Because then I do O of n work for each n node, that's n squared work. N squared is just not allowed here. The problem is really just get the node that has the shortest outgoing path. Essentially the most centralized node. Hey, sorry about that. My Advent of Code Day 23 video just finished processing. This is for this one right over here, and so I just have to take care of that and make sure that I start uploading it to YouTube while I am recording this video. So sorry about that there. But yeah, let's keep going. Yeah, so this is a little frustrating where it's like I obviously know what I need to do. So the problem is get the node in the graph that doesn't necessarily have the smallest in degree, but the smallest path in degree. No, that doesn't make sense, right? You could have a path of length 20 million, and that's just only augments your path in degree by 1. Ah, okay. Basically, I want to find the diameter of a singular tree. Right? Basically, it's minimum diameter of this guy, minimum diameter of this guy. Add them together and plus 1. And in a tree, if I made it a tree, then essentially what do you do? It's like either the shortest path, either the longest path. Jesus Christ. Wait, we saw the problem like this before. It either goes through the root node or it doesn't, right? So it's like, if you are given like the root, it's like either it's like, it's longest diameter from this tree or from this tree, or it's like 1 plus through here. Is it okay if we define leaf nodes? Wait. Is it okay if we do define leaf nodes as value 0? Like, we might have wrong information, but as long as we get the right information in the end. No, this is bad because then it's like, oh, 0. Oh my god, what a great path length. Oh. Yeah, it would be nice to know the root of the tree. The root of the tree can simply be made with the node with the smallest in degree. It really has no dependencies. Right? Def get diameter self comma roots. Here we'll say it. Close. What do we return here? Return -1. Pass. Come on. Pass. Oh my gosh. Yeah, because we need the diameter of a tree, right? To get the diameter of a tree, right? You essentially it either goes through the root node or it doesn't, right? So if it goes through the root node, then great. Get the length of the longest path. And then we need to have like a get height function that is recursive. We can do this, right? We need to build a tree. Yeah, we need to build the tree. Okay, I'm gonna restart this problem. Okay, we need to build the trees for tree 1 and tree 2. We can define the root node as the node with the smallest degree for either tree. Then, once this is done, we need to find the minimum, the smallest diameter of each tree. The result then will simply be diameter 1 plus diameter 2 plus 1. The sum of these two diameters and plus 1 for the edge connected in between. There we go. Okay. So here we need to do def build tree. Self, comma edges. Root 1 self dot build tree with edges of 1. Build tree with edges of 2. Step 1, adjacency list. Get the in degrees, get the reach node. Remember, this is an undirected graph. Adjacency list, comma degrees, default dict of set, default dict of int. For a comma u comma v in edges, list of u dot add v, adjacency list of v dot add u, degrees of u plus or equal to 1, of v plus or equal to 1. Node with smallest in degree. make that the root node. Okay. Now, this will be the root node, so we will make the relationships no longer undirected, i.e., we need to give each node direct children and differentiate their old bidirectional relationships into parent-child and child-parent relationships. Child relationship. Def init self, it'll take in a val, sure. Where it's ID, right, basically? There we go. Yeah, so the hint in this problem is that these are trees, right? And we need to build the tree. That's kind of the hint. Once this is done, this is over, right? We want, like, you know, the node that has, you know, the shortest, longest path and so on. Basically, once we build this into a tree, boom, just get that diameter, right, baby? And there we go. Visited equals set. Here we need to do visited.add that root node. Q is equal to collections of root val. visited vals. We'll say yeah. Oh yeah. We will just make it simple. For neighbor n neighbor val and adjacency node val. Okay, sorry, I'm very focused. Okay, for neighbor val and adjacency list of node val. I always brain fart in these moments. Oh my gosh, okay. Okay, for neighbor val and adjacency list, yeah, for each neighbor, if it's not visited, add it as visited. Then, let's make it a node, and yeah, add it into the queue so that it can be populated. But also, this node's child is its neighbor. So yeah, for this node has a bunch of neighbors. Each unvisited neighbor becomes one of its direct children, right? These direct children that weren't visited before, they're gonna get visited and so on, blah, blah, blah. And the point is that visitation is because, it becomes a parent, right? If anything, here we'll do a self.parent. Neighbor node dot parent. Put a node, if anything. Just so that we have that in there. Right, but this is a lot of information. Okay, visited val is equals set. Yeah, add the root val with the node and the val. So here maybe we should just do roots. Node val equals node.val. There we go. Otherwise, yeah, add that neighbor. Create a node. Benefit for visitation. Make it a child of the node, and there we go. Cool. Cool. And so yeah, they only get added once when it's yeah. So then we can just do turn roots. F string root 1.val equals children, and let's look at his direct children. $45. Yeah. Now we just add the neighbor node and that's it. It's my fault. Yeah, root val is one that has just a child. So yeah, here we'll do a DFS. So yeah, so here we'll do self root comma d depth comma dictionary. Here we'll say not root return. Otherwise, self.dfs for child and root.children. Self.dfs the child. Here we'll do with depth plus 1. D of depth return. Here we'll say d is equal to this. Self.dfs from root 1 has a depth of 0. Yeah, this will take in a dictionary, the same dictionary. We'll do return d. D is equal to a dictionary by default. D is equal to self.dfs by default, this is equal to a default dict of it. Sorry, of list. Yeah, so level 0 has 1. Level 2, or yeah, here we'll do depth of, so yeah, so this is good. So essentially it's saying that 1 is the root node. Fine, make it the root node for all I care. But yeah, level 1 has this one. Level 2 has just 0. And level 3 has both 2 and 3. That's what we like to see. For case 2, it says that, hey, this is oh gosh. Uh-oh. Are all the values unique? But yeah, the no values are unique technically. So we could make this a set. It's just weird, like you should only visit one thing at a time. Oh, maybe for each child? Yeah, that's fine. So now if we look at something like this, then yeah. So essentially it's like, you know, here is level 1. Level 2 is just a 0. Level 3 is this 2 and this 3. Level 4 is this 4, 5, 6, and this 7. So that's exactly what we want to see, which is great. Okay. If anything, this would be a set. Okay. This is good. So now we've basically built a tree. We're able to build a tree. Let's do it for root 2. Which one did I pick for root 2? Picked 1, yeah. So it's just going to pick the, yeah. So, I could do less than or equal to, right? And then it would pick, like, let's say 7 as the root node. Right? So for this one, this is terrible. Wait, how am I doing this logic here? It's just weird to me. Why is saying that level 1 has nodes 1 and 7? This is just terrible. This is frustrating me. Wait, if no roots return. Then I'm not going to add some, right? Yeah. But yeah, if there's no children, don't worry. It won't do it. Maybe it's the fact that I'm doing this passing this dictionary and it's just being weird about it. Right, where I keep returning it and so on. Maybe I do d equals. Over here I say and here I can say or self.d2 and here it's like, okay, here you go, you get a self.d2, right? So here it doesn't return anything. So here we'll say, okay, d of depth.add val. And here self.dfs. with the child and the depth plus 1. And the same dictionary. Oh, was that my mistake? Self.d2 equals default dict yeah, so now it has just S7. Okay, so that's just the issue. Okay, fine. But now at least we have it good, right? So it's like, you know, level 1 has this 7. Level 2 has just this 2. Level 3 has both this 0, this 4, and then 5. Level 4 has both this 1 and this 3. Level 5 has this 6. Hallelujah, ladies and gentlemen. Okay. Yeah, I can make this just less than, but it's fine. I think it'll help us for debugging if I make this a less than or equal, just so that way, like, we make this tree, like, you know, really fun. Right. Now, we have this, right? Okay, cool. Cool. Now what I want a get height function, right? Def get height. Come on node. If not, node.children, return 0, right? And I want this to be cached, right? Return 1 plus max of self dot get height for child in node.children. Right, there we go. Can we do a default? Does Mac support default? Let's check. Python 3, max of this, default equals 0. Okay, fine. Default equals 0. Right, so if there's no children, it'll be, you know, it'll have a height of 1. Right, otherwise, if you have at least one child, that'll have a height of 1. Your height will be 2, so there we go. Okay, nice. Here, just in case, we'll make this a list in case it complains later on. Right, if this was C#, we know you can make it so it's like it has a height field that calls this method every time. There we go. Okay, so now we're able to get a node's height. Okay, good. Idea, we want min diameter in each tree. We should compute the max diameter that goes through a node, for every node in a tree, and then take the smallest of these in the end. Def get diameter node. self, comma node. Height equals self.getHeight of node. The diameter of the node will be the of the node two children with the largest heights. If there are less than 2 children, it's easy. 0 children implies diameter of 1. 1 child. 1 child, logically implies of 1 plus okay. Length of node.children 0, return 1. Well, cache probably not needed to do. Probably unnecessary. For get height, it definitely is necessary. Node.children equals 1. Return 1 plus self dot get height node.children of 0. Otherwise, need two largest heights. You can do this via 2 of n parsings instead of sorting, which is O of n log n. Okay. Let's keep going. Anything here? Yeah. Post child, and here max height of 1 is equal to the child height. Now we'll say the very same thing. What? What did I just do? What? What is going on? Okay, max height 2. Nice, okay. Return 1 plus max height plus second max height. So yeah, caching is unnecessary because this doesn't recall itself, right? Def get smallest diameter from root. Self comma root. Yeah, this is fine because yeah, it does overvan, but it's like, you know, it looks at the children, like it's okay in terms of time complex. Okay, diameter is equal to something to get diameter of root. Okay. So here right now, like the point would be something like this: return self dot get this root 1 plus self dot that root 2, all this plus 1, right? So that would be kind of the goal. Yeah, obviously there's going to be some mistakes here. Yeah. Here's fine, I don't care. We can convert this into a list. There's only one element. Oh yeah. Okay. You want, what do we want here? We don't necessarily want diameters. Yeah, it's an underestimate. It's crazy. Saying that each of them has a diameter. The leaf nodes are gonna have a diameter of 1. But that's not really true. Maybe here we do 1 plus that. To indicate 1 more level. Maybe let's not focus on diameter right now. Let's just do something like this, maybe. No, not quite. Wait. Yeah, it's just gonna be 1 plus the height. Yeah. The leaves have a height of 1. This is the problem. Right, but that's why I want to disinsinuate that, right? 1 plus that, so it's like, it still has the full path length. No, 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 no. Oh, yeah. Okay. Actually, yeah, what we want to do is return. Here we can do get height, def, get depth, self, comma node. This will also have a cache. Something like this. No, huh? I'm on the right track here though. So, right, because like for node like 0, no, 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 no. Mate, okay. Oh. Sorry, I'm like very, very focused on this problem. We have a tree that starts from 1. So 0, how do we know, right? Its parent was 1. So we want, like, from the parent, get its depth. That's a path. Otherwise, get of its children's path, right? This should really be 0 and return 1. All right. Yeah, path upwards from the root is just 0. Path upwards from 0 is just 1 plus the root 1, which is 0. Yeah. Actually, yeah. We should make it return -1. It's actually good. That way we do 1 plus -1 is 0. Okay, cool. Yeah. Yeah, here we'll say get diameter from node. Case 1 equals self dot get depth, or self dot get depth of node. So from this one it should be 1. So 1 plus this guy, which is 0. So this is just not needed. 1 plus that, yeah, so yeah, sure. Get diameter. Case 2 is equal to the children's, right? And then 1 plus the max height. We're going to take this. for child and without children. This is wrong, really? Damn. Really? For every single node, you either go to the path with its parents. We go through one is children, right? I was sure that that would work. But this is a path of one. Diam 1. String. Diam 1 equals. Diam 2 equals. Dang, I really thought that would be it. 4 and 4. Maybe there's a problem with this, right? Let's see. What's height returning? So if you have no children, it's saying it's a height of 1, right? So here we should do maybe -1. This one passes, this guy doesn't. Oh, 0, 1, 2. Alright, get height. Here's to say that this is a height of 2, right? So if something has no children, then, oh my gosh. Yeah. Equals 0. If it has no children, then the longest path from there is 0, so return 0. Otherwise, get depth. Right, if you're the root node, your depth should be 0. Otherwise, it's, yeah. Ah. physical. Sure, we don't need to visit outside this tree. Okay, there we go. We still got a wrong answer. Honestly, at this point, I don't get it. We've built a tree, right? This is a root. Its maximum height. Actually, no, we want to do the minimum one, right? Min. Okay, it does work. Okay, oh my gosh, q.extend children. Okay, so this does work. No.children. Oh, hallelujah, please. Okay, submit. Does it work? Fingers crossed. Is it too slow? Wrong answer? 301 out of 723. Oh boy. Okay. Three to zero. 3 to 0. 2 to 1. So 1 to 2, 2 to 3, 3 to 0. So here we have essentially 1 to 2, 2 to 3, 3 to 0. What's the smallest length diameter in this? It's gonna be either the 2 or the 3, right? And it's gonna be 2 in there, no? Diam 1 equals 2, yeah. Alright, so adding an edge from there would be, best case is you do the 2 or the 3. And so then you add an edge from there, so that's good. And then the other tree, so I'm guessing it needs a diam of 4. Oh boy. 0 to 1. 0 to 4 here. 3 to 5. 6 to 3. 7 to 6. 2 to 7. 0 to 2. 8 to 0. Which is the guy up there, as well as to 9. So this 0 really has, you know, a 1 here. There's a 4 here. Right, so what's the root of this tree? We're saying the root is 9. Okay. 9's height is 1, 2, 3. Here this is 1, 2, 3, or 1, 2, 1, 2, 3, 4. Here it's 1, 2, 3, 1, 2, 3, 4. So yeah, I should have a height of 4. So yeah, this should be returning a diameter of 4. Why isn't it? I wanted to do max path length equals print a string separator turn diam 1 plus diam 2 plus 1. So it thinks from 4 I can do something cool. Here says, no, 1. Oh boy. Oh, I see. Because here it's like, yeah, I got no children, and my daddy's daddy is just 3. But from my daddy, it is 1, 2, 3, 4, 5. I see. So that's the thing that I'm missing here. Okay, I need to debug that. So if we look at my parents, Okay, I gotta think about this case hard. Maybe I just do heights. This is, yeah. Okay. This is difficult. Okay. Yeah, another case that I must, yeah. Obviously here, it's like, if you go up to this part, it has an infinite chain down here that cannot be ignored. So yes, 7 correctly, that's 4, yeah. Maybe the diameter of each node is essentially max between its height plus its depth, or just this one where it's wrong. If I submit this, by the way, how many do I get right? We should have a height. Maybe, what if we do something like root val is fixed at 0 no matter what? Not necessarily the smartest idea, I guess. Because that worked in the other problem. What's nice with something like that is essentially you get this plus that, but in this one, essentially it should be like, you know, three and one, eh? 2, 2, 2. Get depth. Zero. Yes, this is the problem. So maybe I do it at the one with the largest degree. I just know everything is wrong. Yeah, because this guy has a depth of this and a path. Oh my gosh. So maybe building it as trees was wrong all along? Bruh. Okay, I mean, I've made a valiant effort against this problem, but I guess I think it's just, it's time to look at the hints, right? At this point, it's like, okay, I'm starting to doubt that, like, you know, the tree idea that I made is actually worthwhile or not. So honestly, plus I need to use the restroom. So honestly, what I think I'm gonna do is I'm gonna go use the restroom. We're gonna come back, we're gonna look at the hints, and we're gonna try this out to the rest of the problem. So for me, it'll be a few minutes, but for you guys, I'll see you in literally just 1 second. Okay, hey there, so sorry about that. I'm back. Okay, so you know what? Yeah, we were doing a bunch of stuff with trees. Yeah, so I was doing a bunch of stuff here. I don't think it's working. I think I need to start opening some hints, right? So like some ideas is like essentially like reconstruct the tree and so on, build it from like a root and its children, make the root the one with the smallest in degrees, and then it's like from there it's like, you know, try to get the pass. But like it gets annoying in these types of cases where like, you know, 3 is the root, right? Where it's just like here it's like it seems like there's a path of length 2 from the 0. It's like, you know, from its parent and down there's like a length of 2 and so on. So like, yeah, these are not good. So honestly, I should be able to just do like, you know, I should be able to do the max diameter. Right, like what I had before. If length is equal to 0. Return that. -1 maybe. I comment this out. Yeah, something like this. Yeah, exactly this. Right, maybe we can think about this more deeply. No, this should not be the case. Well, okay, let's do this. Get diameter from a node. Turn 0. Oh, maybe it's +2 actually. At this point, I'm just playing with random stuff. No, it should be 1 plus. Alright, because it's, you need to go the child's max height, +1 to yourself, +1 to the other child, and then down. So yeah, this should be 2 plus max height plus second max height. Then is this a 1? No. This is correctly 0. If you only have one child, it's 1 plus that. This should also be this. Maybe 1 plus that. Yeah, and then you get back to these cases of, it's just, yeah, okay. I at this point, I think it's just gonna be wise to just open the, to just start revealing the hints, because I'm at a point where I'm stuck. I have tried not necessarily many ideas, just like one big idea and then like little side ideas from there and so on. But at this point, yeah, well, I don't know about the word stuck. It's just that I'm really deep into a direction and I want to make sure that I'm either in the right direction or not, right? Like I'm very deep in a specific direction and I want to make sure that I'm not tunnel vision on the direction when I shouldn't be, right? Or, you know, if I am, then it's like, good, okay, then I can keep pushing down this path. But I don't want to go into an infinite spiral where it's like, you know, I built the tree wrong in the first place and so, or I shouldn't have built the tree by n degrees and so it's like, yeah, you know what I mean? I need to figure out, am I down the right track or am I not? So I think it's smart to start opening the hints now. So we'll just get started right away with hint number 1. Holy crap. Okay. Jesus Christ, this is like the largest hint I've ever seen. Suppose that we connected node A in tree with node B in tree 2. The diameter length of the resulting tree will be the largest of the 3 following values. The diameter of tree 1, the diameter of tree 2, the length of the longest path that starts at node A, and that is completely within tree 1 plus the length of the longest path that starts at node B. That's completely within tree 2 plus 1. The added 1 in the third value is due to the additional edge that we have between trees 1 and 2. So it can be the diameter of the trees themselves. In the case you add something that makes it irrelevant. But then how do you get the diameter of a tree? But this is just wrong. Or max. Well, no, you're always going to add diam 1 and diam 2. Yeah. Yeah, this is essentially the idea I had. Interesting. Okay, not quite. Yeah, this makes sense to me. This doesn't make sense to me. Okay, let's open up another hint. Values 1 and 2 are constant regardless of our choice of A and B. Therefore, we need to pick A and B in such a way that minimizes value 3. Makes sense. If we pick A and B optimally, they will be in the diameters of tree 1 and tree 2 respectively. And the diameters. The longest path between any two nodes in the tree. Is it not always value 3? You take the longest path between any two nodes, or no? Or no, oh yeah, so if you connect them in the random spot, it could still be the diameter in one of the trees. I see. Oh, that's kind of insane. So we should do it based on length. Wait, okay. Wait. I think I am kind of on the right track in a way. Okay, we're looking at hint number 4 as well. A is the center of the diameter of tree 1 and B is the center of the diameter of tree 2. I see. Grab the diameter. So it'll essentially be the root at some point. So yeah, center is easy because essentially you'll define a diameter between, like, you know, it's path to the max child. Well, it depends. If like one child is much deeper than the other. Interesting hints. We definitely need to be able to get the diameter of a tree correctly. Yeah, we connect node A and node B. We want to make that, like, essentially it's like, yeah, take the longest diameter, go into the middle. Make an edge and do it based, I see. So really, it's just going to be like, you know, diameter tree 1, diameter tree 2, or it's really just going to be the diameter of tree 1 over 2 plus 1 plus diameter of tree 2 over 2. Oh, although from here we can do a single DFS, right? Interesting. Okay. I think the hints are definitely much well needed. I definitely needed these hints. Okay. Okay. Okay, all I need to do is find the diameter of a tree. Can I do that given the edges? I can't compute the shortest path between any two pair of nodes. It doesn't just work. Man, LeetCode has no chill, eh? Okay. Christmas time, you just get a heart that's gonna beat you up left and right, eh? Merry Christmas, they said. Jeez. Okay. I just need to be able to get the diameter tree. This is simple enough. Is it not just the idea that I wrote? It's gonna be like out of... It's either gonna be you take out of your children the two with the largest heights, take those, then it's one edge to you and one edge to the other kid. So here there should not be a 1 plus. Yeah, let's comment that out. Okay, who's texting me via Discord right now? Oh, Noah. Okay, let's put my phone on airplane mode. Sometimes I forget to do that in my videos. Here says the maximum diameters of length 2. So yeah, from 3 to 1. Here 1. It's going to be the max of these. It's not going to be the best result. You want to constrain the 3. And the one that's least constrained is the one that's going to yield to the answer. So yeah, so the problem is not with these. We actually have a working get max diameter in tree. This is actually a working function. Working function. This is a function that legitimately works and it makes sense. Here's get diameter from node. Yeah, this makes sense. Or 1 plus that, or 2 plus the 2 children. This is a working function. So my error this entire time has been in actually... So what I've been doing is essentially saying, hey, here's the maximum path right. So my mistake is I've been trying to maximize this diameter. I'm an idiot. This entire time, my focus has been like, get the longest path in tree 1, connect it to the longest path in tree 2, and that way you have the maximal possible diameter. They want the minimum diameter, not the maximum diameter. But get smallest length. No. I've been trying to do this right. It's like, yeah, I do the maximums, but I try to take the minimum of them all. So it's like, essentially, I was like, get all the paths and like essentially take the minimum of them all. No. I was trying to do this right. But in my logic, I wasn't. And yeah, so now hint 4 is kind of just spoiling us, right? It's just like, okay, if you want to find the, case number 3, A is the center of diameter tree 1, B is at the center of diameter in tree 2. Yeah, something like that I don't expect to work. Yeah, because what happens if I can't just get the route that they pass through, right? I gotta get the center. If the heights are equal, it's yourself. If the heights are in balance, you gotta get the one that has like the deepest child height. Okay. Yeah, it makes sense, right? It's like you essentially have the longest path, which is like, if you do any node, the point is, the reason why it's this way, it makes sense now, but like the point is that this tree is one strongly connected component, right? So you got to be careful. If you pick a random spot, you're gonna end up probably going through the longest path. So what you want to do is take the longest path in the tree, and the best thing you can do is go to the middle. So that way, essentially, you're like equidistant from absolutely everything, right? If anything, I could probably do this. Math.seal of this guy. Math.seal of this guy. Yeah. So I was on the right track, but yeah, I definitely needed that little nudge. Like yeah, this is Like, obviously, everything is giga obvious when someone tells you the stuff. But yeah, to come up with, again, it's like, you know, I'm a big percentage of the way there. Just, I don't think I'm able to do, like, you know, get to the last little bit of the nudge on a lot of these LeetCode hards, right? Because then I start gaslighting myself of whether I'm on the right path or not before I try to, like, fully lock in. So yeah, I mean, like, you know, before we get cocky, let's make sure that we submit and see if we get any wrong answers. But probably not. Hashtag prints. Can we still run this? Yep, let's submit. We might still have a wrong answer, so let's check. And there we go. Completion streak 161 days. Consistency is key. See ya tomorrow. Okay, and we have an extremely slow solution. Holy crap. What do people have? Oh, am I slow because of my computer lagging right now? I don't even know if y'all can hear me. Holy crap, it's so slow I can't even see what's going on here. No, I don't want to see other people's solutions. No. I just want to see the times. I think I saw 400 seconds. No, I don't want to see other solutions. Okay, stop. Okay, yeah, this is... Okay, yeah. So we're 10 times slower than the average. Okay, but we can do a lot of code cleanup. So let's do that and get to work right away. Yeah, so we build the tree. This is useless. This is useless. Yeah, so here we avoid a lot of work. Okay, so we shoved off a full second. So yeah, so let's make sure. We'll do this. So yeah, we don't need this. If I get rid of this, yes, if I get rid of this, I'm still have a working solution. Yep. So I don't need these. I wonder, if I make root val, can I make it anywhere? If I do this, does this work? Can I just make it generally any node? And it doesn't matter? I guess so, right? You just might have a crap load of children and that's all. That's it, yeah. We actually TLE. Interesting. What if I do 1? Oh, TLE because I removed the cache decorator. I'm dumb. Maybe that's why. So let's re-put that bad boy back in there. Which means that, yeah, we can get rid of this. We can get rid of this. List, here we can probably do append. And append. Random.round int 0, length of edges. There we go. Nice. Okay. Yeah, so we're definitely not a fast solution per se, but yeah, we cache get high, so it makes that part fast. Building a tree is just completely necessary. Pick any node as roots. We don't need parents here, right? Okay, yeah, we don't need the parent nodes. Return 2 plus sum of right, so if we do that, does that make things faster there? Maybe a little bit. But yeah, we shouldn't do that this way. Okay, tree. Few comments down there at the ends. Yeah, we don't need to do this. That is a working function, just implicitly by the fact that we're getting the right result. Okay. go. Okay, I think we have a working function. It's just that, yeah, it's just giga slow, but I don't mind. Submit. Bada bing, bada boom. There we go. I'm just happy to be done, and I got advent of code in less than 2 hours and so on, but it just feels nice to be done with the daily and caught up with advent of code. I can finally get like an hour or two, just rest and purely relax my brain off of LeetCode and advent of code and chess and weekly contest challenge and so on. I definitely needed a little bit of a break, so that's big news. And I mean, okay, advent of code 24 probably gonna give us a big surprise, just like LeetCode is, but it is what it is. At least that'll be done in 2 days. This hopefully, you know, LeetCode hopefully will calm down after Christmas comes, which will be tomorrow, and yeah, we'll get back to nice and good business. So. Nevertheless, enough yap-yapping. So, as always, in all my videos, I do a quick recap of how I was able to solve the problem. So for this one, you know, a lot of stuff happened. I tried a lot of my own ideas and so on. At the very end of the day, I was only able to solve this problem because I came here and I was able to look at these hints. And essentially, they made me realize something that I didn't realize, which is like, there's really 3 possible cases for the maximum diameter. Because what's going to happen is you want to minimize the maximum diameter, basically. And so really what's going to go on is my first instinct was like, okay, essentially I need from every node, I need to know the longest path from that node, right? Because essentially I need to know what is the longest kind of path inside of the tree. What I thought was going to happen, I don't know why this was in my mind. Essentially it was going to be like, okay, grab the node that essentially has like, you know, the least path that comes out of it, right? So it's like, for example, it would be 0 in this case, right? Because here it's like, you know, there's a distance of 2, distance of 2, distance of 1. Its maximum distance is 2, right? For something like 4, its maximum distance would be 1, 2, 3, or 1, 2, 3, 4, right? So 0 is the node with the smallest, you know, max distance away from it, right? And so I thought it's like, okay, grab this node with the smallest max distance and pair it with the other node in tree 2 that has the smallest max distance. But I turned out to have a lot of trouble doing that. And that was the main idea that I was trying to implement. Reading the hints, I kind of switched gears in terms of how I was going to do it. I realized it's like, okay, I still do need the diameters of the trees, but for different reasons than I thought. The reason being is that the diameter of the trees might literally be the answers themselves, right? Like, let's say, you know, the maximum diameter is here, right? And it's like so large, like say it's like 10 quadrillion, right? Then like what you could do, like let's say it's 10 quadrillion this way. Then it's like, okay, you can put a node from, let's say it's 10 quadrillion this way and 10 quadrillion this way. Well, you can just put a node from here to here, right? And then it's like, okay, like here it'll be 10 quadrillion plus 1 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 versus 10 quadrillion plus 1 plus another 10 quadrillion. Obviously, the diameter is still going to be this 10 quadrillion plus 10 quadrillion. Adding an edge from here to here actually had no effect on this guy's diameter. So that's why something that I missed is that the trees themselves diameters might actually be the solution, right? Because it might be that one of the trees' diameters is so large that you're able to pretty much pick one of its nodes and pair it with a node in the other tree, and the other tree is just so irrelevant that it's just like, okay, it's just not going to consider this path as long as you put it in a smart place where it doesn't go inside and continue the length of the 20 quadrillion nodes in the row, and there you go. So if you're clever, it could be that like, hey, the maximum diameter just remains unchanged. It's just the maximum diameter between tree 1 and tree 2, right? Otherwise, it's like, okay, the best thing that you can do is essentially it's like, okay, if you're going to connect 2 nodes, they call the nodes A and B, right? So at the end of the day, you're going to have to pick a node A in tree 1 and a node B in tree 2 and essentially put an edge between them, right? Let's think about the longest path, the new potential longest diameter that would create. Well, if you take like a node A inside of tree 1, let's say it's this 0. Let's say node A and B are the zeros. Well, essentially it's going to be the longest path away from 0 plus 1 for the edge plus the longest path away from this 0, right? So here in this case, it would be the 2 plus 1, 3 plus 2, 5, right? And so that's kind of the idea. And I thought that was all you needed. I didn't realize that, like, hey, you know, one of the tree's diameters might actually be the maximal one in the first place, right? I did not realize that. And Which, dang, yeah, like, you know, pretty clever problem. Again, everything, like, you know, hindsight is 2020. Everything makes sense when it's like, oh yeah, you see the solution. It's like, well, duh, obviously this stuff is the way that it works. But trying to discover that as you solve the problem is pretty tough. At least for me, it's pretty tough. And so, yeah, I gotta admit that is pretty tough. But it does make sense in terms of, like, you know, explaining the solution. It's pretty easy because it's like, you know, everything. It makes sense in hindsight, right? It's just like, oh, obviously, right? If I had 10 quadrillion going this way, 10 quadrillion go this way, then it's like, yeah, I can put that little irrelevant little edge that's going to affect nothing, and there we go, bada bing, bada boom. So yeah, the answer is either, like, you know, the diameter of tree 1, the diameter of tree 2, or, like, you know, given a node A and B, essentially it's like, okay, longest path away from A plus that edge plus longest path away from B. Now, the thing to consider is that, like, okay, these graphs, you essentially have n minus 1 edges, right? So there's n nodes, m nodes, n minus 1 edges, and essentially we're told that this forms a tree, right? So what does this mean? That means that the graph cannot be disjoint, right? There cannot be a node that's alone and not connected to every other node. And also, there's exactly n minus 1 edges with n nodes, or exactly n minus 1 edges with m nodes, which means that, like, there's not going to be, like, any looped around cycles. So it is cyclic, this graph, just because the nodes are undirected, but otherwise, if these edges were directed, then essentially this the graph cannot be cyclic, right? So essentially, it's like, you know, it's guaranteed to have that nice property. I don't know if I was able to leverage that at the end of the day, but given that, it's like, okay, well, what that really means is that, hey, since it forms a tree, so really it's because there's a tree, essentially you're going to have exactly one strongly connected component, right? Every single node is reachable from every single other node, right? So whatever edge you pick is essentially going to be like, okay, again, you're essentially going to want to pick the one that minimizes, like, you know, the path away from this. Well, let's say the longest path is of length n, right? The only possible spot it can be, the optimal solution, is in the middle of this path, right? Let's say that essentially the longest path is of length n, right? So this is the longest path, right? If you put the full graph forms a strongly connected component, right? Every single node is reachable from every single other node. So if you take your node n prime over here, or your node u here, all of a sudden there's a path. Okay, let's put some spaces in here. There's a path of this length, right, which is definitely more than n over 2, right? Or if you put it, like, on this right side, then there's this path of this length over here, as well as this one, right? So there's a length that's greater than n over 2. But if you put it in the middle over here, then all of a sudden you have a path of length n over 2 here and a path of length over 2 here, right? Because what matters is essentially the length of the longest path coming out of that node. Doesn't matter the length of the other paths and so on. All that matters is the length of the longest path. So if you want to minimize that value, you must put it dead center in the middle of the longest path inside of the entire graph, right? For example, here it will be between this 1 and this 4, so you want to be in the middle of that. The only two middle ones are this 2 and this 0, right? But there's also this path over here, right? So actually that's 1, 2, 3, 4, 5 nodes, 1, 2, 3, 4. So the longest path is actually here. So actually the 0 is the direct middle node of it, right? So it's the center of that path. And so what I wanted is essentially the one that minimizes this maximum path. Well, it's essentially going to be grab the maximal path, i.e. the diameter of the tree, and essentially go to the center of it. So that's why hint 4 works, right? A is the center of the diameter of tree 1, and B is the center of diameter of tree 2. By going to the center of a diameter, you're essentially picking that node that does have, you know, minimal, maximal, like, the minimum maximal distance away from that is reachable from that node, right? So like 0, for example, can reach a distance of 1 going this way, a distance of 1 plus 1 is equal to 2 going this way, or 1 plus 1 equals 2 going this way, or 1 plus 1 equals 2 going this way, 1 plus 1 equals 2 going this way. So the maximal value of all of these was 2. And again, this is the value you want to minimize. And so if you want to minimize that value, you better pick, you know, the longest path in the graph and the node that is directly in the middle of it, right? That's kind of the point. And so if that's the case, essentially we're able to grab let's say for now we know how to grab the maximum, the diameter of a tree. For example, here it'll be this guy and so on. All we need to know is its length, right? Because then what we can do, so here's like 1, 2, 3, 4. yeah, four of, there's 4 edges in here. So here in this case, it's like if we divide the length by 4 by 2, we essentially get 2, right? And it's like, it makes sense. It's the length 2 plus 1 at the edge plus 2 over here will make the 5 that we need over here, right? Now, if there was an odd amount of edges, or like, an even amount of nodes, then essentially we would do +1, right? Because essentially, let's say there is an odd amount of edges, like for example here we added 1 extra edge, and now there's a path 3 and a path 2, right? So the maximum one will be length of 3. So that's why in my code here you'll see that here once I get the maximum diameter values, I'll essentially divide it by 2 and then take the ceiling of it, right? Because if I get like, say like 2.5, right? Because it would be like 1 edge plus 2 plus 3 plus 4 plus 5 is 5 edges. The best way that I can split 5 edges is essentially 3 and 2. So it's like, I can't do 2.5 and 2.5. It's like I'll be screwed. I'll have 2 and 3, like, and so I have to pick the 3 because it's the larger one. So that's why I do math.cl here, right? Math.cl this one, math.cl for the tree 2, and then 1 edge to essentially connect those 2 together, right? And that's kind of the point. And so here, bear with me in terms of how I get the diameter here. So essentially I build a tree from my edges for root 1 and root 2, and from edges 1 and edges 2, and then from there I essentially get the maximum diameter from root 1, get the maximum diameter from root 2, and then there's only 3 possible options, right? The same as the hints gave you. It's either max diameter 1, max diameter 2, or grab this guy, divide by 2, essentially, so that it's essentially the node with the smallest maximal distance that it can reach. And its actual maximal distance plus the same thing inside of tree 2, and then you take those two paths and you're going to connect them together with an edge, and so that means that's why you get this +1 over here, right? And so you take this result, the maximum of this result, and this result, and that's what we return. Now we can go into how we actually wrote the build tree and get maximum diameter entry functions here. So at the very beginning, inside of my build tree function, I used to do it where essentially I made the root of my tree the one with the smallest integer. Turns out that's completely irrelevant, and you can just make it any single node. So, all right. The reason why is because even if you pick a node like 2, which looks like it definitely couldn't be the root of a tree, yes, it can. It just means that 4 is one of its children, 7 is one of its children, 5 is one of its children, and 0 is one of its children that happens to have more children. That's it. And so it's like, essentially it's like, you can grab the 2 and essentially like, these are its children under it. It's just that it has one child here, one child here, one child here, one child here. That's it, right? So really, you can just make any single node that you want your root, and there's no problem with that. And so yeah, that's something I didn't realize until I started getting accepted, and I was like, oh, okay, it makes sense in hindsight now that it's accepted why that works. Otherwise, here what I do is like, okay, I get a list of edges. So here's the build tree function for both edges 1 and edges 2 that they essentially pass you. Again, remember like these edges. There's n-1 many for the edges 1 and m-1 many for edges 2, and essentially like the node values can be from 0 to n-1 or 0 to n-2, and those are the values inside the edges. So essentially it's like, okay, for every single u, v, and edges, it's going to say like, okay, there's an edge from u to v and from v to u, because these are undirected edges, right? This is undirected trees. So once I build my adjacency list, essentially what I do is like, okay, let's pick a random value to be like my root here, and here, you know what, we can just, we'll just make it 0, just because why not? There we go. We'll always just make it 0, right? If we submit something like this, you'll see that it works just fine. My solution is just super slow. I'll still go over it, but at least it works, which, heck yeah, there we go. So yeah, let's just run this bad boy. And there we go. So here, essentially what I do is like, okay, we want to populate the tree, right? So given a list of edges, let's populate the tree. Well, now we have an adjacency list. So what do? We say, okay, we're going to have a set of visited vals. We're going to add the root val as visited, because essentially we're populating a tree from the root. We already know what value we want with the root. We want it to have a value 0. So really it's like, we can make this root, yeah. So yeah, we just add root val in there. And then here we have a double-ended queue that contains the root, and then it's like, okay, well, the length of the queue is empty, keep popping something, and then it's like, okay, loop through all of its neighbors, right? And all of its neighbors that are not yet visited, right, are essentially going to become its children. Why is it important to do the not yet visited? Because when I get to those now going to be children later on, one of their neighbors is going to be that parent, right? And so we need to make sure that, like, okay, when it gets to the point of adding your parent, like, as one of your potential neighbors, as one of your children, you don't want, you know, the parent to have the child as his child and the child to have his parent as the children, right? So that's why we keep track of a visited set. It's like we recognize the fact that, like, you know, every single node that points from one to the other will point back to itself. And so it's like, okay, that way it's like, you know, when you add a bunch of children, you'll put it in this visited val set, because here you'll append them in the queue, and when you get rid of them in the queue, you pop them from the queue. You don't want to add those same values back as your children, because those are your parents, right? So you can't do that. So that's why we keep track of this visit set. But otherwise, this is just very standard. We're just going to keep populating the tree as we go. So here we're going to pop the node from the queue. At the beginning, it's just the root. And then it's like, okay, for every single neighbor that's not visited, i.e. that's not either my parents or grandparents or whatever and so on, that's not been put in the tree yet, we're essentially going to add that as one of my children, right? So here we put in visited. We're going to make it that new node. And here we're going to be like, okay, let's add that into the queue so that we can populate that guy's children later on. But otherwise, our current node's children, we're going to add this neighbor node, right? And at the very end of the day, once I build my full tree, I return root. So that's essentially how I build the tree. And then here I have a get height function, very, very useful. Given a node, I will essentially say like, hey, every single tree node, by the way, when I say build these trees, so like tree node of neighbor val, I created my own class here, tree node. Essentially, it just takes a value, which is like, you know, the node value itself, whether it's 0, 1, 2, and 3. I could probably get rid of it. It's actually not necessary, but yeah. So actually, it's not unnecessary, because in my queue I only use the nodes and then I get the value from there, but I guess I could pass in the node values inside of here as tuple, so it doesn't really matter. But the point is I get the nodes values inside of here, inside the tree. It has a parent value, which I actually don't need anymore, so if I rerun this, we'll see that it works. But otherwise, I have its children as a hashset right over here. If anything, I could probably make this a list, right? And here I'll do node.children of 0, and here we'll do children.append, right? And so here something like this could probably work. Yeah, so I didn't need to make the children a set there. There's just no need. Okay, and that shaves us, like, you know, another 1,000 milliseconds and so on. So whenever you can use a list over a set, you might as well. Okay, cool, good to know information, right? And it's like here I can make some other optimizations. Let's equal to 1. Return 0, not node.children, else this, right? And so here we can run this again. Blah, 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 blah. Nice, nice, nice. We shove another 300 ms. Okay, so it's like we could keep doing those tactics over and over to shove off the temp complexity, but why bother, why bother, why bother? But okay, so yeah, so now we essentially have the build tree function. So all I need to show is this get max diameter in tree. So how do we do this? Essentially, it's like, okay, we want the maximum diameter in the tree, right? Let's think about it. The maximum diameter essentially has to go through some root node, right? Where it's like, essentially trees are a recursive data structure where it's like, you know, you have a node, you have all of its children. Each of these children essentially has its own tree and so on. So at some point, the largest diameter of the tree essentially has to, you know, like say go from some node over here, go on to one of its roots, and then go on here, right? So the point is like, you know, the diameter is essentially the longest path between any two nodes, right? Essentially those two nodes at some point must share some type of parent, which can be one of the nodes itself, right? Imagine you have the root over here and the node over here. It's like, obviously this guy's like, you know, parent chain, this node is up here, right? Otherwise, if they're separated like this, it's like, okay, you know, they eventually meet up at a parent that's all the way up over here, right? And so essentially the maximal diameter in the tree will essentially go through one of these roots, right? So that's the main idea. So essentially the maximal diameter of the tree is either, okay, the diameter that goes through me, the maximum diameter that goes through me as the current root, or otherwise out of all of my children recursively call the same thing, right? Because maybe it's either goes through me or it goes through one of my children, but recursively, because for each of those children, maybe it doesn't go through them, maybe it goes through one of its children, etc., etc., etc. If it's the case where it goes through me, here's how we do it, right? Solve the get diameter from node. Well, essentially, if you wanted to do it in a binary tree, the way you would do it is either like, you know, it's gonna be like, you know, if you're the only node, right, then it's 0, right? That there is no path to your left and no path to your right. If you had a child but no right child, then it would just be 1 plus, you know, the height of the left child, right? Otherwise, if you only had a right child, it would be one edge to the right child, so 1 plus the height of the right child, right? Because it's like all the way up to how deep it gets, right? Otherwise, if you had those two children, essentially it would be like, okay, 1 plus the height of my left child, and then 1 plus the height of my right child, and so then I coalesce those two together, and so that they can meet at my root, right? If this is my root, it's going to be one edge plus the height of my left child, and then here one edge plus the height of that right child, right? Here I have multiple children. I can have 0 children, I can have 1 children, I can have 2 children, but I can also have 3 children, 4 children, 5 children, 6 children. I can have a lot and a lot and a lot of children, right? So now let's think about it. If we have multiple children, well, again, a path can only like come to us and then out of us, right? So it's like, essentially it's like a parabola if you think of it that way, right? So it's like, you know, kind of like this, where it's like, you know, if here's your root, it's like there's going to be some path here, and then it's connected through here, and then it goes down here, right? So the point is that essentially you're going to go down to one of your children, go through you, and then to another one of your children. So what do you want to do? Essentially, if you have 2 or more children, you only care about the 2 children that have the largest heights, right? Because those contribute to the longest path. You essentially want the longest path here plus the longest path here. If you have no children, there is no path here, there is no path here, there's a total of 0 edges, right? So if length of no children is less than or equal to 1 and not no children, i.e. you know that you have no children, then return 0, right? Because here there's no path this way and no path this way. If you only have 1 child, then it's going to be like, okay, there's going to be 1 edge to that child plus the height of that child. That's it. So that's why it's like, otherwise, here's 1 plus the height of get the only child I have, right? Like you have length of 1, get the child at index 0, and just get its height, right? Self that get height, I think we covered it. Otherwise, we can cover it quickly afterwards. But otherwise, it's like, okay, if you have 2 or more children, what you care about is 1 edge here plus the maximal path from here, so essentially the child's height, and then 1 edge here plus, you know, the length, the maximum path over here, which is essentially this child's height. Right? So essentially you want the 2 children's heights, right? So grab the 2 max children's heights. So at the beginning I say, okay, let's grab the max child and its max height, the max height and the corresponding child, right? So for every single child and know that children, get the height, and if it's greater than max height, then good. There you go, bada bing, bada boom, right? Otherwise, it's like, okay, then we want the second max height. So now we're going to loop through all the children again, and child height, we're going to say is equal to, we're going to have that child's height, but then we're going to say, okay, if that child height is, you know, bigger than the current second max height, but only if it's not equal to the max child, then we're going to set that second max height, right? So essentially we grab the 2 children's with the highest heights, their heights themselves, right? And so once we grab the children with the maximum height and the children with the second maximum height, which might be equal values, who knows, then we have all the information we need. And what do we want? We want 1 edge to one of the children's and then its height, and then 1 edge and then to one of its children, 1 edge to one of its children, and then its height. So it's going to be height of this child plus 1 edge here plus 1 edge here plus height of this child. So that's height of child 1 plus 1 is 2 edges plus the height of that child. So here that's why we do maximum height of the first child, maximum height of the second child, and plus 2. So it's like 2 for this edge here and this edge here, and then maximum height child here and second maximum height child here. That's kind of the point that of the reason why this returns that, right? And that's the whole point. And then for get height, essentially, by the way, I put a cache decorator here because it's like I might get the height of a node many times. So I only want to compute it once and then make it an O of 1 operation every single time that I get it. Essentially, it's a very easy function. If you have no children, you have a height of 0. That's it. There's no path under you. Otherwise, it's going to be 1 plus the height of out of all your children, the one that has maximal height. That's literally it, right? And the reason I make this cache is that way. It's like, you know, once I get my own height, I essentially go down the chain of all my children, and I essentially populate all their heights and so on. And then whenever I call get height again, I essentially have that as an O of 1 lookable value. So essentially, like, I will only like traverse all the nodes once, and then from that point on, every time I call get height, it's just O of 1 operations for getting that node's height, right? So it's like, you know, I only have to do the computation once in total. So it's like, if anything, I could pre-compute all the heights right away and just store those inside of the children. But here it's just, I made it a function called get height so that I could keep calling it, and I could put it cache, right? But otherwise, one thing I could do is essentially populate the tree with heights, right? Start from the root node, you have a height of well, actually you need to go down from the leaves and work your way up, right? So it's like I could use parent, whatever, right? But yeah, so this is just the way that I did it. I have a get height function, cache the results so they can be O of 1 once I populate them for the rest of the problem. And here we notice that if I actually comment this out and I don't cache my values, we're definitely going to TLE. For sure. It would be impossible not to. Impossible, because we call this so many times that every single time. So we basically turn this from an O of 1 operation to an O of n operation every single time, which we just straight up cannot afford, right? So yeah, here we TLE, we put cache red back on this bad boy, and we'll see that now we pass this with absolute flying colors. There we go. So yeah, so very, very slow solution, but a solution nevertheless. And honestly, I'll take any single break that I can get at the moment, because it's been maybe a little bit too much LeetCode for me, we'll say. But point is resilience, so it's okay. I don't mind it, but if I can get away with an accepted, then that's all I need, especially for a difficult hard problem where I kind of relied a little bit on the hints to find the little last aha moment of how to be able to do it. But hopefully that summation makes sense. So now that I've explained these methods, the point is very simple, right? Get the maximum diameter in tree 1 and tree 2, and then again, for the same reasons as I explained, it's either like, whoops, that is not what I want. It's either going to be the diameter of tree 1, diameter of tree 2, or essentially like, you want the nodes that have like, the minimum maximum path away from it for both tree 1 and tree 2, and then put an edge between them. And as we explained, the node that will be that is essentially grab the maximal diameter in your tree and essentially the center of that. And so what it's, all you need is the length of the diameter, because essentially you'll just divide it by 2, and math.ceiling, because if it's of length 5, right, the maximum diameter, then from here it's like you'll have a length 3 and a length 2, so 5 divided by 2 gives you 2.5, rounded up gives you 3, which again is that length 3 over here, and that length 2 over here. Otherwise, if it's even, you'll have like 2 this way and 2 this way, so it's just like 4 divided by 2 is 2, so that's the right answer. So that's why I have this math.ceil. Otherwise, again, it's like diameter of tree 1, it could be the answer. Imagine like, a 6 had like 10 quadrillion nodes going this way, and 4 had 10 quadrillion nodes going this way, then the answer would be 10 quadrillion plus 1 plus 1 plus 1 plus 1 plus 10 quadrillion, right? And here, if you add an edge from 5 to the 5 over here, it's like, it's going to be 5, so it's going to be 1 plus 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 10 quadrillion is going to be completely irrelevant to the current diameter of this guy, which is 20 quadrillion plus 1 plus 1 plus 1 plus 1 plus 10 quadrillion, right? So it could be that adding the edge between the two trees actually has no effect on tree 1's diameter or tree 2's diameter, right? So you grab their initial diameters, because those could be the possible values, or otherwise essentially it's like, you pick intelligently where you're going to connect the edge, and then from that get the new result of the new potential maximum diameter, which again is like, if you're smart, it's essentially you're going to take the maximum diameter, you're going to go down right at the dang center of it, and so that way it's like, the longest path away from that node is math.ceil max diam divided by 2, and then same thing for this one for the tree over here, and then you add an edge between there, so that's why plus 1 for that edge, and then these values for each of the tree, because you picked that node intelligently. So hopefully again, like I got that information for the hints, so the hints were actually kind of super helpful here, but yeah, hopefully with that this solution makes sense. And yeah, but otherwise that is pretty much it for the video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment, but otherwise I'll catch you in the next one. So until then, ciao my friend, bye bye.